Alright, so it looks like we're up and running again. This is the second half of worksheet. I did run into a little trouble with one problem. I lost my train of thought, so I'll cover that immediately. And that's over here at, I forget what number it was yesterday's work. But we were looking at the area under the curve 1 over x, but I was drawing the ln function and looking from 2 to 3, and I knew the numbers weren't working, and I couldn't figure out why. But so I lost my train of thought. So it's under the area of 1 over x, and you know this is approximately 0.4. For if you do those first 50 lesson sets from Algebra 1 to a little bit of trig, you're familiar with that. If not, I guess you got some work to do. And so 1 over x from 2, this is a half. Right, the altitude on the left, I'm doing a little trapezoid here, which will overestimate just a little bit. The altitude on the right is 1/3. Width divided by 2, so 1/2 of 5/6, 5/12, which is a little bit bigger than 0.4. Just showed some work there. So the area accumulation here produces a function, produces the ln function. So from 1 over t dt, not that I'm going to do it right now, but 1 over t dt from 1 to x is another way of writing the ln function. And be developing that further as we go along. All right, so this is a little meatier, 18 problems, 19 problems coming your way, than the previous 19. So I'm not going to rush it too much. But at the same time, I just want to recall that what I talked about yesterday, you're not learning it immediately. You're going to learn it over a period of time. Each problem we'll look at just for a couple minutes and then go to another one and then another one. But then we come back to it and talk about it again. And it's that patience and reflection that I think will serve you well. I don't know how this camera is working. As I say, I'm not in a classroom anymore. I don't get to put the problems on the board. So it's going to take a little longer to read a problem, put it on the board. But if you're looking for some practice and you're looking to go up the ladder in this discipline, you got to struggle. It's the students who struggle that make the most gains. It's students who give up on the processes and don't continue to think about them. In other words, don't struggle. And I had a colleague say that last semester, and I'm saying it now because I think he's right. All right, so thank you, Peter. I think you're right. I wish I had heard that phrase, that it's the students who struggle that make gains in math, much earlier than prior to retirement. All right, so here's an implicit differentiation problem. I think it's problem number 19 on the sheet that I'm not even going to show anymore. So x squared minus 3x y to the fourth plus y squared equals 10. How can we look at rates of change when we have relationships like that? And it turns out, I wish I had René Descartes, but over here, you know, we started with that familiar x squared, x times x squared. How's it changing? We've done an awful lot of work with numerics, and I suggest that you look at some of those videos because I think it's the drawings that help you understand this process. And so the accumulation of area is just a layering process. Now I have to show dx point, you know, things like 0.01. Pretty hard to draw that. So I'm saying a small difference in x, all right, will give us more area. Okay, and there's patterns to it. Well, I could have done it with y. I could have said y squared equals area. And then I would have had a dyyy and another dyyy. And symbolically, I mean, that's what you're looking at. So that's what we do with implicit differentiation. Now, I could have changed this to, you know, minus 3x y to the fourth. And that's what's going to happen in this problem over here. And so it's not dy anymore. It's 4y cubed dy. And this is going to be minus 3dx. Okay, and this is going to be y to the fourth, the old length, and then this one's going to be minus 3x, and we've got a little bit of a product rule going here. So these problems here usually take students several days to make any sense out of what's going on here, even mechanically. But a month from now, we will go right from line 1 right to the answer, and it'll be a 5-second problem. Not yet. So these are differentials, 2x dx. So I'm not going to draw it again, but it's dy, the change in area, equals 2x dx for the squaring function, right? And it's when you divide by dx, that's when you create the derivative of x squared. So there's an intermediate step that I'm not sure we show often enough. Let me get my eraser. Okay, and I already did this one out because I knew it would take quite a while, and I know this video is going to take probably 40 minutes at least. But I think you got to have the initial conversation. So 2x dx, then drawing that rectangle, we can see the two parts of the layering. Minus 3, I'm looking at that, minus 3x times y to the 4th. So derivative of this, minus 3. Dx, that intermediate step, times y to the 4th, minus 3x times 4y cubed dy. I think I drew that a minute ago. And then we got y squared 2y dy. Now, dy, you can cut down on the amount of writing. You can write that as y prime. So there's a dy here, and what I did in the next line is I divided everything by dx. And if you do, that cancels, and then you create your y prime here, right? Dy dx we're going to call y prime, just to speed this process up. All right, and now we're all algebra. Okay, that's a flimsy board. So, positive 2x becomes minus 2x. Minus 3y to the 4th goes to the other side. And if I'm multiplying by minus 12x, then I'm at y cubed. I can divide by that, and then I can divide by that. And now I have a way of finding rates of change on this curve at any instant by that formula. And you don't have to doctor it up. Leave it like that, and it's just the mechanics of it. And hopefully the conceptualization over time will come into focus better for you. Okay, but it's not going to happen until we start conversations. So we started a conversation. All right, next problem here was actually the one I butchered. I said I would show you how you solve that. On the last video, it was dy dx equals y, which is really 1 times y. So I put that 1 in there so you could see the integration with an initial condition of 0, 4. These types of problems you can solve in 5 seconds or less as we go forward as well. Okay, and most students can. Right now you're probably shaking your head going, oh, don't worry about it. So we separate the variables. So if this is times 1, multiplication by y on the right, division by y on the left, and I move the dx to the other side, and then we integrate both parts. Integration. Another way of writing division by y is 1 over y times dy. And so this becomes 1 dx, 1 over y. It comes from the ln function. So the ln of the absolute value of y plus c1 equals x plus c2. What's the derivative of x? 1. So always going up. Y equals x is going up at a 1-to-1 ratio. All right, so we can put the c1, c2 together and get c3, and let's just call it c. Now we're back to algebra. How do you solve ln functions? E to the, all right? So the absolute value of y can be a plus minus on the other side, e to the x plus c. E to the x times e to the c is another way of writing, right? What is m squared times m to the 3rd? It's equal to m to the 2 plus 3. So hopefully you can see addition came from multiplication. And e to the c we'll call quantity a. So we have a e to the x. Now you put a 0 in, and you can see 4 e to the x. All right, so let's erase that and go to the next problem. So as I say, this is going to be a little cumbersome because I can't move around the room quickly because I don't have a room to move around in with whiteboards all around it. All right, so I'll do work here. We'll move this over so I can see the problems quickly and easily. I don't know what I'm dropping here, but dropping like flies. All right, so let's put this here. Let's put this here, and you'll have to bear with me on this video because we're not going to be able to take too many shortcuts until we get more familiar with the material. All right, I'll have to put the glasses on for this. All right, so what's the next problem? Oh, minus 2x plus 4 plus 5. Okay, so I'm giving you an absolute value. Minus 2x plus 4 plus 5. And I want to know what's the rate of change at x equals, I forget what I said, at x equals 1,000. All right, so what's the rate of change of this function? Anytime I give you absolute value, if I want you to find area under the curve, or if I want you to find rate of change, draw it. So we have a V shape down, we've got negative 4, 5, and I'm looking at this side. Okay, well, we did a ton of piecewise value problems on those first 50 Algebra 1 and trig lesson sets, and the reason was so we could handle this with ease. All right, so what's happening on this side? I'm increasing. On this side, I'm decreasing. Looks to be a constant rate. I hope that if you change that, you're seeing the branch that's on the right-hand side. All right, and if I was doing the branch on the left, I'd be going up at 2, and then I'm going down at 2. So you can put 1,000 in here and figure out where you are, do y2 minus y1, but hopefully, as we go forward, you just recognize that you're going down at 2 to 1. Okay, and that gets that conversation started. Next problem. Maybe this won't take forever. dy dx equals minus x over y. dy dx equals minus x over y with an initial condition of 3, 4. With practice, you'll recognize this hopefully as the implicit differentiation, and it will be a circular relationship that we look at. But let's separate the variables. This time multiplication on the left, division of y on the right, multiplication on the left, division by dx on the left, multiply on the right. Let's integrate both sides. We get y2 over 2 plus c1 equals x2 over 2 plus c2. Let's put our c's together and make it c3, and let's just call it c. Now's a good time to put a 3 and a 4 in. So if I put a 4 in, I got 8 on this side. I've got 9 halves on this side, plus c. And so I'm going to bring the 9 halves to this side. I've got 16 halves minus 9 halves equals c. Let me make sure I put the 3 and the 4 in properly. 3 squared, 9 halves, yep. So that's 7 halves, I believe. Right here, yes, so 7 halves. Okay, I feel like I'm making a mistake here, and I'm not sure why. So let's multiply everything by 2, and we get, oh, this was a minus x squared with 2. That's my problem. Okay, so plus c3, c, sorry for the mistake. So minus 9 halves becomes positive 9 halves. This is already 16 halves equals c. There's your 25 halves. All right, so now we're here. Careless mistake, but not going to start all over again. All right, so now they're multiplied by 2, and you've got x squared plus y squared equals 25. Why don't we do a quick implicit differentiation? 2x dx goes 2y dy. Those are differentials. This is not changing. Okay, let's divide by 2, and we get x dx plus y dy equals 0. Do you remember the next step? Divide by dx. This dx cancels. That shows up. What are we going to call that? We're going to call that y prime. How do we isolate y prime? We move the x to the other side, and then we divide by y. There, you got a little extra practice on implicit differentiation. So, we got a circle, 3, 4. What am I doing? According to the formula we just created, the minus x over y gets me minus 3/4. Does it look like that slope might be going down 3 over 4? I hope so. All right, conversation has started. If you want to dive into it a little bit more, I'm not doing a video tomorrow, so you can go look at implicit differentiation on the playlist. Go to the calculus playlist, and I think I spelled this out a whole lot more clearly and slowly, just that topic. So feel free to maybe do that tomorrow. Okay, next problem. Limit as x goes to 5. of x squared minus 25 over x minus 5. I hope you're not using L'Hopital, and I hope you're looking at this more deeply and more reflectively than just the algebra. Right? We know the algebra, x plus 5, x minus 5 over x minus 5. The x minus 5's cancel, we drop in a 5, and we know our answer is 10. But the question is, can you see this as a derivative? X squared, 5 gets me 25. Can you see it as a y2 minus y1 over x2 minus x1? For instance, if we go to 7, 49, well, then we've got an average rate of change of what? 24 divided by 2? If I did that properly. So, you know, from 5 to 7 is an average rate of change of 12 to 1. Well, we want to get closer. If we're talking about a derivative, we want to get a value closer. So let's move to 6. Let's move to 5. Of course, I'm doing a one-sided limit right now. 6 gets me 36. Well, that's 11 over 1. So I went from a slope of 12 to a slope of 11. Is it believable that I'm going to go to a slope of 10? Well, I've got to get an x that's what? Really close to 5. Like 5.001. And if I square that, I get 25.010001. And there's your 10 to 1 limiting situation starting to appear. So this is actually y2 minus y1. There's your y2 minus y1 as x goes to 5. That's what I'm hoping we can see over the course of time. And do I think you can see it immediately when you first start studying this stuff? Not unless you're gifted. And I'm not gifted. I'm just a regular old high school student who didn't understand calculus in college, ended up teaching this material and kept asking questions like, why does this work? And 45, 50 years later, I can see some of the reasons why these things work. Because of repetition, seeing the material. So trying to get you a lot of repetition here. All right. Find the area bounded by x squared. Y equals x squared and y equals minus 2x plus 15. Which implies, there's an implication here, that we want to look at when does x squared equal minus 2x plus 15? When does x squared intersect with minus 2x plus 15? 0 gets me 15. Well, how are we going to find this area here? By an infinite number of rectangles. And what's the change in x? Well, that's going to be our dx. And what's going to measure the height? Well, we have two curves. We have minus 2x plus 15, and we have x squared. Just like we have two altitudes, for instance, 9 and 4. What's the difference? No, I think it's 5 units. And ask yourself, how did your brain do that? You took the top value and you subtracted the bottom. Now they're changing. Those values depend upon where you are on the x-axis. For instance, if I was at 1, then x squared is a height of 1, and that's a height of 13. Drop in a 1, right? And so they don't intersect here, but I can see there's 12 units of height on this particular altitude. All right, so what are we going to do here? We're going to erase a little bit, and we're going to do our Algebra 1 skills. We're going to solve this for the point of intersection. And we can see that they intersect at x plus 5, x minus 3 equals 0. So at 3 and 5. So we're going to integrate from negative 5, from negative 5 to 3. And we're going to take the top function, which is minus 2x plus 15. We're going to subtract the bottom function to get each of those altitudes. And we're going to give those altitudes a little bit of width. And we're going to add them all up. We're going to get an exact answer. And I'm not going to take the time to do that integration. Well, minus 2x comes from minus x squared. 15 gets me 15x. Minus x squared gets me minus x to the 3 over 3. And we'd have to drop in minus 5, and we'd have to drop in positive 3, and we'd have to do a lot of straight math. But right now we're just trying to get the concepts discussed. All right, and so we started a conversation. Next problem. When is big F of x going up? If I give you, when is big F of x going up? When is it increasing? So we have big F, little f, and F prime, mimicking position, velocity, acceleration. That's where we're going with that in a little while. And I'm giving you F of x, which is the derivative of big F. And what does the derivative measure? Slopes at an instant. And if I want to be increasing, I think my slopes have to be positive. So I am looking at minus, where am I? Minus x cubed. I have minus x cubed. Already running out of ink here. Minus x cubed. I'll change swords in a moment. Where am I? I'm here. Let's put the dot there so I can find that quicker the next time. X minus 5 squared. I suppose I could have made anything up here. Next time maybe I will. X minus 4. That's what's on the sheet. All right, so what do we have here? We have roots at 4, and that's an odd exponent, so I'm going to get a sign change, which means 4.001 minus 4 is positive, 3.999 minus 4 is negative, and 3.99 or 4.1 has no effect on the sign of that term, and nor does it have a sign effect on that one. But it does have effect here. So I'm going to get a change of pace, and because I put in a big number, this is going to dominate here, this minus sign, so this is going to be heading down. So I also have, oops, sorry, that wasn't the biggest value here, 5, that should have been over here. All right, and the other one is 0, and that's odd. Odd, even, no sign change, odd, sign change. Okay, so now I've got a graph that looks like that. I could have done a little better job of showing the cubic rate change there, okay? So now when is this increasing, big F increasing? When its derivative is positive, these are positive y values, so those slopes of big F are positive from 0 to 4. And they're also positive nowhere else. Now, if I wanted to write this, I think probably more clearly, I think that would be the way you should get your final answer. So between 0 and 4, big F's going up, unless I made a careless error. Hopefully I didn't. All right, there, I can find this quicker now. X to 2x, 2t dt. Just mechanics. X to 2x, 2t dt. Okay, we can call these dummy variables because this is going to become a function in terms of x. This is going to get us some function on the right. What do we want to call it? Well, 2t dt is the t squared. That's how things change. Right, there's your dt, there's your t, there's your dt, there's your t. Right, that's the layering process for this. So that's coming from t squared, and we got to put an x and a 2x in there. So 2x squared is 4x squared, dropping in an x, x squared. So this is actually another way of writing the function 3x squared. Interesting. You give me your rate, a couple of parameters, the way of writing a function. Interesting. Oh boy. So if I know grandma's rate on Route 91, I can track her. All right, grandma needs help on Route 91 now. So, can you write the slopes of tangents using derivatives? So, I'm going to give you y equals x cubed, and I'm going to tell you that x equals 5. I'd like you to write using a limit, something that expresses the rate of change of that function at that x value. That's what we did before. It's the limit as x goes to 5 of y2 minus y1 over x2 minus x1. All right, a little review of how do you factor those critters. You factor those critters by x minus 5 times x squared plus 5x plus 25. And that's getting divided by x minus 5. So what do we have here? We have x squared plus 5x, all right, and 25 plus 25, let's see. Oh yeah, so when I put in 5, all right, I get 25 plus 25 plus 25. I don't have my magic box with the sleeve, but notice the 3 squares, and what's the derivative of x cubed? 3x squared, and so I'm adding 5 units of surface area on 3 parts of the box. I should have had my box with me here, but that's happening. And another way to write this would be the limit as h goes to 0, and we'll talk about that one another time. 5 plus h cubed minus 5 cubed all over x plus h minus x all over h, and I just put something in your brain, and we'll talk about it another time. All right. So we'll be a little bit further along the next time we talk about it. But I don't want to show that right now, because I know there's another problem like that coming along, and I can show it then. All right, so solve dy dx minus 2x over y. So dy dx, why don't you stop the video and see if you can do this with an initial condition of y of 0 gets you 10. God, I hope I'm seeing all of this as I work here. I think I could bring this way a little bit. Okay, well, bear with me. It's a whole new process, and repetition's my friend. And I wish I had a cup of coffee. All right, so you pause the video. I'll just do the problem. I think we're going to get an ellipse. All right, so we got our y dy. We got our minus 2x dx. Integrating gets us y2 over 2, bringing our constants to that side, minus x squared plus c. We can find c now by putting in a 0. So c is equal to 100 divided by 2, which is 50. And now, once again, we can multiply everything by 2 and bring this to the other side. So we get 2x squared plus y squared is equal to 100. Okay, hopefully I didn't make any mistakes there. So 2x squared becomes 4x dx. This becomes plus 2y dy equals 0. And now we can divide by dx. That cancels. That becomes y prime. That's still 0. And now we can move the 4x to the other side, which is minus 4x. We can bring the 2y to the other side, which is 2y. And I think we can see our relationship of minus 2x over y. So that's finding slope. You're going to use an x and a y value to find the slope on this curve. Where's the curve? On this curve. And that's the manipulation of that, mostly mechanical practice at that point. So that's solving a differential equation. All right, let's approximate ln of x, the area under the ln of x curve from 2 to 5. I think that's where I had my Freudian slip, 2 to 5. I think I had looked at this lesson set, read the problems through, just to get a sense of what I was looking at. And that's why I found the area under that curve versus under 1 over x. All right, so what do we have here? Let's approximate it with a trapezoid. Okay, the trapezoid's going to underestimate this just a little bit. Okay, and we're going to use, not integration, but we're going to do 2 left-hand rectangles. All right, so left-hand rectangles means that I'm using this altitude on the left and this altitude on the left to get area 1 and area 2. And all we have to do is write the calculations. We're not actually going to do it out. So the altitude on the left here is the ln of 2. And because I'm bringing this up into 2 equal parts, then this is 3.5. I'll use 3.5. All right, and so what's my width? Well, my next altitude is the altitude of ln of 3.5. We'll use a decimal here. All right, so those are my two altitudes, and I have to multiply that by width divided by 2. And my width is 7/2. Let's write this as 7/2. Instead of that, yeah. All right, and let's write 2 as 4/2, just for now. So what is my width? I can see it's 3/2, and I have to divide that by 2. So what do I get? 3/4. And I don't know what the ln of 7/2 is. I mean, I could find it quickly enough. It's the ln. No, I don't. I don't know the ln of 7. So let's bag that. All right, so that is just what's called a Riemann sum, using little rectangular areas to approximate area under a curve. We can kind of see where this develops, I hope. Now, if we, that's a trapezoid. Oh, wait a minute. I just did the trapezoid. I butchered that. So what I wanted to do was left-hand rectangles. My fault. Left-hand rectangles, so I got confused here. From 2 to, is just that altitude, that width. 1.5 units. That's this width. Times this and that. So that's the left-hand Riemann sum. If I'm going to do a trapezoid, then I've got 3 altitudes to consider here. All right? And the one in the middle gets used twice. So what I get here is I have to do that one twice because it's shared. And then I have one at the end. One at the end, which is the ln of 5. You can tell I haven't been practicing this in a lot of years. All right, so now that's where that 3/4 comes from, because it's the width divided by 2. All right, and that's what's called the trapezoidal rule. And we'll just do them, you know. We'll do another one on Monday, we'll do another one on Wednesday, so on and so forth, and Friday. Probably do 2 lesson sets a week, which is probably 4 days of videoing, with a day in between, that you could maybe look at the trapezoidal rule. There's tons of them on YouTube. Tons of practice with left and right hand rectangles, Riemann sums. I told you this would take a little while, this lesson set, to get us up and running. And now we're going to use linearization to approximate 63.9. I'm going to do 64.1, easier for you to see. So we're going to approximate the square root of 64.1. And we're going to use a derivative to help us. So we're going to look at the function y equals the square root of x, which I hope you understand is x to the 1/2. Hope your skill level's allowing you to see that. Let me change markers here. Let's see if that helps. I'll find that cap later. Otherwise, it's just going to dry up. So I am going to use the square root function. And I know something about 64. I know the square root of 64 is 8. So I got a position on root 91 here. And I'm going to try to find 64.1, but I'm going to draw a line here. What line did I just draw? The tangent to this function at this location, because I know the value at that location. And I know the derivative. I asked you to memorize the derivative of x to the 1/2, 1 over 2 root x. So I can write that equation now, the tangent line. I know 64 gets me 8, and I know that I'm changing at square root of 64 is 8, 1 over 16. So when I drop 64.1 in here, which is 64 1/10, and I subtract 64, I get 1/10. And now I think I have a pretty good approximation of 64.1. It looks like it's 8 and 1 over 160. And I'll bet you that's within 1,000th of a decimal place of a correct answer. All right, so that's called linearization. Fancy word for we wrote the equation of a tangent line, which I think we're going to get pretty good at. So we'll see that one again soon and worry about learning it over a period of time so that it's effortless learning. You know, no big deal. We don't have to have it today. Hopefully you're going to come away with some more understanding than you had the day before. All right, now let's use U substitution to do the following problem. Now these come from the chain rule. These types of problems come from the chain rule. And we want to be able to integrate them. So what have I got here? I've got a 4dx. And I'll just show you a mechanical way that's going to get us an answer. All right? I'm going to let, and it takes practice, it takes trench work, just doing them over and over and over again. And we aren't there yet. But I'm going to let the letter U stand for x cubed minus 1. All right? And I am going to look at the differentials. The change in U comes from 3x squared dx. And so I have a way of writing dx now. I have a way of telling you a new way of saying that, and that's du over 3x squared. So I'm going to write this as du over 3x squared, and I have a new way of writing x cubed minus 1. And that's simply u to the 4th. Little substitution. Now I got some algebra here. 3x squared, 6x squared, what you can learn is that fits into that twice, and I can actually take a constant out of the integration, and I'll show you why maybe in the next video, because this is getting kind of lengthy. U to the 4 du, well, I know what that is. That's u to the 5 over 5. And that's going to get what? Multiplied by 2. And I got a little constant here. I'll talk about that in more detail later. And now I can replace u with x cubed minus 1. And if you take the time to do that, so that's going to be x cubed minus 1 to the 5th power. Doctor that up so you can see it. So if you take the derivative of that, you'll see how you get back to that original using the chain rule. Maybe I should do that for you just quickly because you're just starting to learn the chain rule. So the 5's are going to cancel and it's going to drop down 1. So that's my first step. Multiply by 5 and drop it down 1. And then we have to multiply by the derivative of what's inside, which is 3x squared. And I feel like I'm making a mistake here. And I'm lost in my thoughts. So I shouldn't have done that. I'll come back to that because I'm not going to take the time to sort it out. As soon as I stop the video, it always comes to me. But right now in front of the camera, it might take me a minute to figure it out, and I'm not just going to do that. All right. So f of x concave down. So we've got f of x, we got f, and we've got f prime. And I'm going to look for concave down, and I'm giving you f prime of x. Again, so we're looking at second derivative. And so when is it concave down? When second derivative is negative. We'll talk about why that's true in a minute. X minus 5, x plus 4. So I have a cubic and it's acceleration here. So let's look at acceleration from the easiest function we can think of, which is probably x squared. Right, so x squared, first derivative 2x, second derivative 2. What do you notice about 2? It's always positive. What do you notice about x squared? It's always concave up. All right, so that's just a quick putting something into your head. So what do we have here? We got roots that are changing, sign changing, because they're all to odd exponents. One of them at 5, one of them at 0, one of them at negative 4. All right, so we've got a cubic that looks like that, because when I put a number bigger than 5 in, I'm heading to positive infinity, the bigger the number. All right, so concave down when I'm negative. When am I negative? Negative infinity to negative 4. Union 5 to infinity. All right, that's when this function is concave. Oh, I want it down, right? Yeah, so that's when this function is concave down over those two intervals. Okay. And I'm not going to integrate this. This is an x cubed. So this is going to be an x to the 5th function. All right. But I'm not going to do that integration. Take too long. All right. We'll see if this helps anybody. If it doesn't, I will stop doing these videos. But hopefully A month from now, we're going to be in a good place. So a of t equals 4t minus 4. So we got a little acceleration with respect to time and an initial condition of v of 0 equals 5. So it's just a differential equation here. We're going to find v of t through integration, and x of t we'd integrate again if we wanted position, but we're after velocity. So this becomes v of t becomes add 1 divide 2t squared minus 4t plus c. Very quick and easy. Throw a 0 in, you get a 5. Right? So another way of writing a v of t would be the integration 4t minus 4 dt from 0 to, I guess I'm going to do dummy variables here, 4m minus 4 dm. Don't expect you to follow what I'm doing now, but it'll come into play down the road. That's another way of writing v of t. And I'm not going to try, yes I am, 4m minus 4. Okay, so if I start at 0, I get negative accumulation, positive accumulation, and we'd look at that accumulation to get us this function. All right. So if I got negative accumulation until I get to what? Some number here. The negative accumulation is slowing down till I get to a slope of 0. Then come back up. Now where did that happen? Minus b over 2a at x equals 1. Or t equals 1. And then we would get faster and faster accumulation, and I hope you start to see that curve emerge. Okay, so we just looked at that from a graphical standpoint. We may not have really talked about that before, but we're layering our discussions with deeper discussions. And we'll learn it slowly over time. All right, we've got about 3 more problems left. Find the area under the cosine curve. Y equals cosine x from 0 to 2 pi. 0 to 2 pi. All right, let's get a look at the cosine curve from 0 to 2 pi. Okay, positive accumulation, negative, positive, and they're going to neg each other. Not that I drew it that well, but they're going to neg each other. So we're going to get 0 for an answer. Okay, so if y prime, I'm finding the area under cosine. Yeah, so you can think of it as y prime. Then we're going to create the sine function. And we're going to go from 0 to 2 pi, cosine curve, dx, which is the sine of 2 pi, minus the sine of 0. Sine of 2 pi is 0, the sine of 0 is 0, and 0 minus 0 is 0, which is what we did when we looked at that area accumulate. 1 period of accumulation. All right, so next problem. Quick chain rule. F of x equals 5e to the 4x. Let's do a quick chain rule. Okay, derivative of e to the x is itself, so f of x is going to have this function as part of its answer. It also has the ln of the base, which is the ln of e, which is 1, so we don't have to write it. If it was some other number besides e, we'd have to have the ln of that base. And we have numbers coming at us 4 times quicker than you thought they were. All right, so that's our derivative of that function. And we'll get to the point where we can do those in 3 seconds or less with practice. Find the local maximum for minus x cubed. Minus x cubed plus 27x plus 5. This is actually graphing form for a cubic. So we really have minus x minus 0 cubed plus 27 times x minus 0 plus 5. Okay? So, minus b over 3a. Well, there is no b term. There is no bx squared term. There's ax cubed, bx squared, cx plus d, right? But b is 0. All right, so that's why I wrote that, because that's in graphing form. All right, so we have a function that looks like this. We know that it's going up at 27 to 1 right here. And that's actually the slope of the tangent at the y-intercept as well. Overlaps with that, so it's 0 gets you 5. Where's our max? Our max is over here. Our local max is over there. How do I get it without calculus? Well, I got to start from 0 plus the square root of minus the slope, the opposite slope, over 3 times a, and a is -1, so -3. And we're going to find that our x value is 3, and we're going to get it from calculus now. All right, so how do we get it from calculus? Well, we recognize that the slope at max and the local max and mins is 0, and we have a particular shape, concave down shape there. So we'll take y prime minus 3x squared plus 27. We'll set it to 0. And if you solve that, you'll see that x equals 3. And then we'll take 3 and plug it into the second derivative, which is minus 6x. And that gets me a negative, which means we have a concave down shape, which means we've proven. And if we drop in a 3, we can get that y value. Now, just putting some thoughts in your head. Using derivatives to find some information. Now, if you want to know how I got that without calculus, then you got to go to the playlist, the cubic playlist, and look at completing the cube, the geometric underpinnings of that process. I think I'm almost there. Yes, I am. That was it. Okay, that was the last problem, and that was kind of a lot of conversation. 46 minutes, woo, one of the longer ones, but we're just starting those conversations, and if we continue to have them on a regular basis, which wasn't happening before, I did 4 lesson sets and then just had to leave the process. But now I think that we can get up and running. I'll get another lesson set off the computer that's similar to this one. We'll talk about those topics again, delve into them a little more deeply, perhaps, here and there, and slowly build up our repertoire. So if you can't get in a classroom, you got a shot at moving up the ladder here, okay? And this stuff is only good if you remember it, which is why we're going to do a little bit of this every day, a little bit of this every day, because that's how you learn things. Okay, enough of my rambling. Back again on Monday.